Introduction to functions. Now a lot of this is definitions at the beginning anyway. So, pay attention. First off, a relation is a set of ordered pairs. Ordered pairs are nothing but points. Points are always x, y. A function is a set of points such that each x value has exactly one y value. We'll do a few examples and this will be a lot more clear to you. Since we're dealing with x values and y values, the domain is a set of x values. Now, what that really is a set of odd numbers when substituted for x yield solutions. In other words, you get an answer. Those answers are called the y values. Those y values as a whole are called the range. Domain are x's, range is y. Domain is x, range is y. So here we go. Determine the domain and range of each relation and determine if a function. So, when we find the domain, we're just going to list, in this case, the x values for the given points. There's 3 points here, and each one of these is of the form x, y. So our x values are 0, 2, 4. At least one, each one only once. And then the range is a set of y values, 1, 3, and 5. Now, to determine if it's a function or not, I'm going to use something called mapping notation, and this actually does make this a lot easier to understand. So what I'm going to do is, I'm going to just draw a couple of ovals. I'm going to call this first one domain, second one the range, D and R. I'm going to throw in the x values for the domain and the y values for the range. Now I'm going to draw a line connecting the correspondence. So the first point is 0, 1. So the 0 corresponds to 1. 2, 3 means 2 corresponds to 3. 4, 5, 4 corresponds to 5. Now all we need to look at is over here in the domain for it to be a function. Because by definition, to be a function, each x must have exactly one y. So this 0 has exactly one y, this 2 has exactly one y, this 4 has exactly one y, because each of these has exactly one line coming out of it. So by definition, this is a function. To the second one. The domain will be the x values. Now as you can see, I have a 2. I have another 2, but I don't need to write it again because I already have it listed. And then I have a 3. Now the range, you'll see the 5 for the y values, a 7, and a 10. That's my range. I'm going to use this mapping notation again. I'm throwing my values for my domain, which are 2 and 3, and for my range, 5, 7, and 10. Now the 2 corresponds to 5, it also corresponds to 7. And 3 corresponds to 10. But take a good look at this. See this 2 right here? It doesn't have exactly one y value. In fact, it has 2 different y values. Because the 2 fails, because there's more than one y value, this is not a function. Remember, each x can only have one y. This is showing the 2 having 2 different x's. It's just a definition. There's no work involved. It's just a definition. Keep that in mind. Now this next one, do the same thing. Domain and range. Now I have a 7 for the x, and a -2 and an 8. Now if you look at the range, you'll notice that they're all the same y value, which is 9. So let's do a mapping notation once again. Domain and range. 7, -2, 8, and my only y value is the 9. So each one of these corresponds to that y value. Now some of you may be thinking that's not a function, but it actually is. The definition doesn't say each y has exactly one x. It only says each x has exactly one y. So each one of these has exactly one y value because each has exactly one line coming out of it. This is a function. Always read domain to range, not range to domain. Domain to range. Now let's look at some other examples. This time we're actually given equations to determine if these are functions or not. Now what I'm going to do, we're actually going to I like to graph them and let you know what's really going on, but I'm not going to. We're going to do some supposition here and just test some points. If I were to let x be 1, now substitute it in, I'm going to get negative 1. And that's the only answer I'm ever going to get for the x value. If I let x be 2, I'm going to get 3 times 2 is 6. 6 minus 4 is 2. If I let x be negative 3, and I substitute it in, I get 3 times negative 3 is negative 9. Negative 9 minus 4 is negative 13. So each time I throw in any x value, I'm always going to get exactly one y value. So this is a function, because for each x I can only get one y value. Now we'll show you an easier way here in just a second, but this is kind of the way you're expected to look at it for now. So this one, if I let x be 1, now throw in the 1 squared minus 4, 1 same as 1 minus 4, which is negative 3. That's the only answer I can get. If I let x be 2, I get 2 squared is 4, 4 minus 4 is 0, and I can't get anything else. There's no other possible thing I can try. Throw in a negative 3, and I square that and I get a 9. 9 minus 4 is 5. If I throw in a positive 3, I get 9 minus 4 is 5. But it doesn't matter about the y values. Each x only has one y value. So no matter what I try, I'm always going to get exactly one answer for each x value. No other possible answers. So this is a function. Now let's try this one. This time, if I let x be, let's just let it be 0, and I substitute it in, I'm going to get 0 squared plus y squared equals 4. So I get y squared equals 4. Now I'm thinking, what squared gives me 4? Well, here's the thing. I get two possibilities. Y could be 2, because 2 squared is 4, or y could be negative 2, because negative 2 squared is also 4. So as soon as I find one instance where when I have an x value, substitute in, I get two possible y values or more than one y value, that tells me that that's not a function. So keep that in mind. But now I'm going to show you actually the easier way. I may come back to these, give you an idea of what's really going on, and the easier way to do it. There's something called, well, let's just do it right now before I tell you what this is called. In fact, I'm going to go ahead and graph a couple of these. I'm going to graph y equals 3x minus 4, because we can graph that one right quickly. Because negative 4 is the y-intercept, slope is 3, so I'm going to go up 3 to the right 1, and then connect the dots. Now here's what that means. Each of these x's, as they go along the x-axis, each of these x's has exactly one y. That x is that y, 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 y. Each x has exactly one y. Doesn't really explain what I'm trying to get at, so I'm going to come over here and I'm going to draw this one. This one is actually a circle. Center at 0, 0, radius at 2. Let me do that. I'll cheat a little bit. Now, here's what happens. You see it when I did my points, I actually used 0, and I got possible answers of 2 and another answer of negative 2. What that means is that if I were to come over here to like this 1, I can go up here and go down here. What that says is, for example, that point will be something like 1 comma some y value, and this point will also be 1 comma some y value, but a different one, maybe a negative 1. I'll just use the ones that I used. This one, this one. This is 0 comma 2, and this point is 0 comma negative 2. What that's saying is that my x value of 0 has too many y values. So does this one right here for the 1. But the thing is, all I need is 1 for one x value to fail. There's something I could do to make it a little bit easier. I could draw a vertical line, say through x equals 1. Anytime I draw a vertical line through a graph and it intersects the graph more than once, that's not a function, because it's like saying that this point and this point have the exact same x value, which in this case is 1, or over here it would be 0. That leads us to the vertical line test. This is the easiest way to determine functionality. That's what I call it. Vertical line test. If any vertical line crosses the curve more than once, then the curve is not a function. Simple as that. Watch this. Anytime I draw a vertical line anywhere, it only crosses it exactly once. So yes, this is a function. I come over here. No matter where I draw a vertical line, and by the way, this isn't going straight down, it's going at an angle. It's a function. Now watch these two. As soon as I draw a vertical line and it goes through it more than once, it's like saying that this point and this point have the exact same x value, and it can't because it's too many y values for the same x value. That is not a function. Same thing here. If I draw a vertical line, say through there, it's saying that this point and this point have the exact same x value. Not a function. Once again, if you were to label this point, that would be negative 4, comma 2, looks like. This would be negative 4, comma negative 2. Negative 4 has too many x values, so only ought to have 1 to be a function. So that's how you determine functionality using the vertical line test. Now let's look at function notation. You're going to start seeing this right here, f of x. What this says is this is a function f in terms of x. This is how you say it, f of x. And f of x is nothing but the same thing as saying y. F of x is the same thing as y. What it means is, it means to substitute the given x value into the given equation, or into the function that f of x represents. It is not f times x. This is not multiplication, it's notation. Notation just means how you write something. There's nothing to work with with this notation right here. Now, I'm going to do this example. If this example doesn't help you, I don't know what will. Got it? Now, we don't have to use just f. We use f because the word function begins with the letter f. It could be g of x, h of x, h of x, whatever you want to use. But most times you'll see f of x. So here we go. We have f of x equals 2x plus 7. Before we do that one, I want to do a slightly different example. I'm actually going to write this one out because it's important enough to write it out. We're going to let y equals 2x plus 7. Then we're going to say find y when x equals 3. And the way you do that is you take your equation, which is y equals 2x plus 3, and everywhere you have an x, you'll substitute it with a 3. You'll simplify it. 2 times 3 is 6, and 6 plus 3 is 9. But look at the wording. There's a lot of words there. And something you keep in mind about mathematicians, they're kind of lazy, so they'll invent notation that will help them write out directions a whole lot faster. That's all this is. This question right here, let f of x equals 2x plus 7, when it asks to find f of 3, it's the exact same question as what we did over here. This f of 3 is going to be the y value found when we substitute the 3 for the x. That's all we're going to do. Substitute the 3 for the x. And 2 times 3 is 6. And 6 plus 3 is 9. And in fact, watch this. Normally points are x comma y. Well, now we can also say they're x comma f of x. It's just fancy notation for the letter y. And so for this one, it would be 3 comma f of 3. Which is just saying that the point would be 3 comma 9, because the y value that we found when we substituted the x with the 3 was the 9. X is 3, f of 3, or y is 9. It's all the same stuff. Just keep that in mind. So let's do some more and see what we can come up with. We got a few more examples here. So now let's, the same equation, f of x equals 2x plus 3. Let's substitute or find f of negative 1. So we'll substitute that in. I'm going to do all the work horizontally. You get -2 plus 3 equals 1. Hey, it doesn't matter what it is. F of W, we're going to substitute in. 2 times W plus 3. That's just 2W plus 3. They're not like terms. Hey, watch this. We can go crazy with it. Let's say we draw a flower. Let's find F of a flower. Well, that's nothing but F of a flower plus 3, which is 2 flower plus 3. Hey, let's go even crazier. You want to? Watch this. F of what's in here. It doesn't matter what it is. We're going to take what's in the parentheses, in this case what's in here, and substitute it in for the x. That's all it is. So please don't make this more difficult than it needs to be, because it isn't difficult. Got that? That's all you're doing when you see function notation. Well, like I said, we can actually use any letter we want to represent the function. And so for this example, it gives you an idea of what I'm talking about. It says that a of x equals x squared may be used to find the area of a square if given the length x of a side. Now if you look at that, you probably remember that the formula for finding the area of a square is a equals x squared. Well, same thing as a function where we use a to represent the function. And we use a because area begins with the letter A. You could easily have used f of x, but I chose to use a to represent the area. And all this means is, if you read the problem, to find the area of a square with a side length of 7 centimeters, well, x represents the side length, and so all we're going to do is what we normally would. It's just a different way to write it out notationally. Everywhere we have an x, we'll put a 7. So we're actually going to find an a of 7, which is the same thing as finding 7 squared, which is 49, and don't forget your units, 49 square centimeters. That's all it is. Just get you accustomed that you may see different letters instead of F. You may see an A, G, H, whatever it may be.